Hello everyone. In this video, we are going to look at axial loading again, but instead of the stress on the plane that is perpendicular to the load, for which the stress is simply P over A, we want to know what happens if the plane is inclined, right? So if you change the angle of the plane and make the angle of the plane rotate by an angle theta counterclockwise here, what are going to be the stress on that plane and why does it matter? I'll let you know once we get to the end of this video. So the first thing is, if I break down the two components of the force on this plane, although on the normal plane there is only a normal component P, but on the angle plane there are two components because this P will be decomposed along normal to the plane and tangent to the plane. We call them N and V, and clearly you see N is P cosine theta, V is sine theta, V is P sine theta. So not only we have two components now, a normal and a tangent, also the cross section of this angle plane is different than the normal plane, and you clearly can see that. Why? Because if the depth of this beam stays the same, but the height of the plane is going to go from this vertical to this one. So if that was H, let's say, this is going to be H over cosine theta, and assuming that this B stays the same, so original A was BH, now this new one is going to be BH over cosine theta. So I can say that compared to the original A, the A of the inclined plane is A over cosine theta. And since cosine theta is less than 1, clearly A is bigger than, A1 is bigger than A. So that's the cross section. These are the normal and the shear components. So we can get normal and shear stress. Of course, sigma is going to be N over A1. So P cosine theta over A over cosine theta. You're going to get P over A cosine square theta. This guy is that sigma x that you had in the axial load. And for cosine theta, we're going to write it as 1 plus cosine 2 theta over 2. The shear stress is going to be negative V over A1 and negative P sine theta over A cosine. You're going to get negative P over A. You multiply by a 2 and divide by a 2. And this is basically, again, sigma x, so negative sigma x. And this guy is sine of 2 theta over 2. So this is going to be the normal stress on that plane. This is going to be the shear stress on that plane. And you might say, why is the shear negative? Well, it's because of the direction. If you look at the direction, when we turn this plane, when the plane is like this was the direction of tau and sigma. Now, if you look at this one, the tau is this way, okay? Because V is downward and sigma is this way because of N. So because this T is, if it was this way, it was positive, but since it's downward, it's negative. That's why you have added the negative sign. And if you plot that sigma and tau versus angle, because clearly you see it's a function of angle, you're going to see these two plots. So clearly, 1 plus cosine 2 theta is always positive because cosine at most can be negative. 1 plus 1 is always positive or 0. And it's only 0 when theta is basically positive or negative 90 degrees, because cosine of 290 is 180, cosine of 180 is negative 1. So at negative and positive 90 degrees, this curve here, that is the sigma on this angle plane, and the shear stress, as you can see, sine 2 theta. So at 90 degrees, it's sine of 180, which is 0, and negative is also 0. And then at 0 is also 0, so you're going to get this curve here. So this is your tau, that guy was your sigma. And you see how they are changing as a function of angle, okay? So far, this is finding them as a function of angle. Now, what's the application of this? Why should I learn this topic? That is the question I always ask each and every one of my students, and those of you who are watching this video, to ask your instructor. Whenever they teach something, ask them, why should I learn this topic? What's the importance of this? So let's look and see, where is it that your sigma becomes maximum? So your sigma becomes max at angle theta equals 0 clearly. On the other hand, your shear stress becomes max or min at plus minus 45 degrees. And the maximum of it is, by the way, half of sigma max, right? So sigma max is sigma x, which is that P over A. Max of tau is going to be what? P over A over 2. Good? So first of all, here you learn something, that the maximum shear stress is half of the maximum normal stress on any inclined plane at most. And of course, they happen at different angles, 45-degree angle difference. Now, what's the importance of this? The important is brittle material. Remember, brittles are the ones that do not extend way beyond the linear region, right? So they extend a little bit and then boom, here they break. They cannot have a lot of elongation. So this material, their structures cannot easily slide on each other, and they cannot tolerate a lot of basically deformations, and they typically fail under normal stresses. And normal stress maximum is what angle? Theta 0. So if you take cast iron or, I don't know, glass or anything, and you apply the tensile test on it, if you look at the cross section of the cast iron, it is going to be at perfect 0 degrees. So the planes are perfectly upright, and that means the theta for them is 0. And so that's why you see brittle material are breaking at perfect cross sections, and it's straight, no angle. On the other hand, ductile material, like for instance stainless steel or aluminum or stuff like that, these material are typically failing under shear stress because their structures can slide over each other, and they slide until necking happens and until the material will fail. So for that reason, if you apply the tensile stress on, or tensile test on ductile material, you're going to see that the necking is happening. And in the necking, if you look at the tip of these cross sections, the angle is about 45 degrees. Okay, so the reason that they get this kind of sharp faces and the angle of the plane of failure is 45 degrees is because this is a ductile material and the maximum shear stress happens at 45-degree angle. So you can easily justify why the cross sections of cast iron, the angle of it is different than the one from a ductile material. Okay, now here to solve an example of a problem, we are going to look at a compression bar here that is placed vertically, and you're applying a force P on it. The width of it is B, the depth of it is also B, the load is 8,000 pounds. And the bar has two pieces that are connected by a glue joint. So literally, you created that angle plane yourself by cutting this part or having two parts and gluing it together. The angle here, alpha, the deviation from vertical, is 40 degrees. And again, they are glued together. Now, the material is a structural plastic for which the allowable stress in the compression and in the shear are 1100 psi and 600 psi. So basically, in this material, the maximum sigma and the maximum tau, or allowable sigma and allowable tau, are those numbers. Yes? Also, the allowable stress in the glue joints is 750 psi in compression and 500 in shear. With everything fixed, the only thing variable is B. You want to know how wide this B without any failure. Okay? So this is the problem we are going to solve. Now clearly your angle here is alpha, and Is that the same as theta? The answer is not exactly, because if you look at it in horizontal direction like this, correct? Remember the angle that we used in this derivation, look at that, that is this angle here. Draw normal to the surface, the angle of that with respect to the horizontal axis is theta. That is how we derived it. So if I go back here and look at this example, I have to create a normal to this glue joint here and then measure that with here. Now remember, what angle was alpha? Alpha was the angle of the plane with respect to the vertical direction. So this is alpha, not this one. If this is alpha and this is 90 degrees, this is 90 minus alpha, and that is the same as this angle that you're interested. Okay, so clearly the angle that you have to use, the theta that you have to plug in into your formula, is this guy here, which is the same as this. This is 90 degrees, this is 40 degrees, so the angle you have to use is 50, but positive or negative, that's another thing you have to pay attention to. If the angle was clockwise measured, here from the horizontal direction, your angle is clockwise 50 degrees. So your theta is actually negative 50 degrees, okay? Pay attention that you have to get the correct angle before you place it in the equation. So you got your theta, theta is negative 50 degrees. What's the next thing? The next thing is, what is sigma x? If you look at those formulas, they have sigma x in them. So I have to calculate sigma x in both of them. And sigma x was simply P over A. Correct? And guess what? P is a given number. P is 1100. And the cross section is B squared, correct? So if I go back and look at it, or 8,000. So this is 8,000, and the cross section is B squared, right? Now what we need to do is to look at these allowable values, and based on those, see how much is the maximum value for sigma x or the minimum for B. So if you look here, it says that the allowable stress for compression and shear of the physical part are 1100 and 600. Now, what should I do with those? Well, should I compare sigma x against that 1100? No, because remember, your tau and sigma are functions of angle. You have to find their maximum, which are these two, as you can see, sigma x and sigma x over 2. We have to compare against these. So yes, sigma x can be compared against maximum normal stress, whether compression or tension, in this case compression, and the maximum shear should be half of sigma x. Yes? So if I go ahead and say, well, sigma x equals to the maximum sigma, and maximum sigma in this case is the same as the allowable sigma for that material, and that number, if you look at it, basically it was 1100 psi. On the other hand, sigma x over 2 is equal to the tau maximum, and tau maximum at most could be the same as tau allowed, and that was 600. So from here, you can see that, let me do this here. So from here, sigma x is 1100. But from the bottom one, if you multiply, you see that your sigma x is 1200. Okay, so these two are for the material that is under compression. One of them gives this much max, one of them gives this much max. Which one would you use? You always use the smaller one, because if the material is safe against compression, clearly from here it will also be safe against the shear. Okay, so you always pick the smallest one. Now, that's not enough, because not only I have these two limits from the material, I should get some other limits from the glue joint as well. The glue joint also under compression and under shear, it has these numbers. Okay, it has 750 psi for compression and 500 for what? For shear. So we have to use those values as well. And based on that, we should also get some values for sigma x. Now, for the glue joint, we cannot say that the maximum sigma and the maximum tau will necessarily happen. Why? Because inside the material, I can have all sorts of angles from 0 to 45 degree to anything. And clearly, I can achieve the maximum sigma and the maximum tau inside the material. So I can directly use these formulas that I got, and I can see what is my maximum sigma. But for the glue joint, the glue is not all over the material. It's only on one specific angle. So for the glue joint, I cannot use these sigma maxes. I have to use these original formulas and use the specific angle for the plane, which is negative 50 degrees. So this is for that material, right? This is for whatever it is. It's the plastic, I guess it's called. This comes from the plastic. But for the glue joint, I have to go with the formula where sigma was, if you remember, it was sigma x over 2, 1 plus cosine of 2 theta, and tau was negative sigma x over 2 sine of 2 theta. And for theta, I have to plug in negative 55 degrees. And say sigma at max could be the same as sigma allowed for the glue, and tau could be the same as tau allowed. And how much are these numbers? Sigma allowed for the glue is 750 and the other one is 500. So this one is 750, this one is 500, and from these two, you can find two other numbers for sigma x. Okay, so let's go ahead and calculate it. So this is going to be 1850, 15, this is going to be 1015 psi. So I got two other numbers for sigma. Now I got four numbers for sigma. Which one do I pick? As I told you, always the lowest one, which is this guy. That is the number you pick. So now you say sigma x, which is at most could be 1050, so everything is safe, whether the glue joint or the plastic under shear, under normal. This is equal to P, which was 8,000 divided by B squared, and this guy was 8,000. So from here, you can easily get B and take the square root of that, and you're going to get 2.81 inches. So at least you need 2.81 inches for this system to not fail. Okay? So you see we got four different numbers from different things, and you see the application of that, right? If you have two pieces and you glue them together, and you know how much your glue can withstand against compression and shear, mostly is the shear one that is important for glue, because under this kind of load, mostly the material will slide. And you see that it's actually this guy that determined everything. The weakest thing that you have in a glue joint is typically the shear, right? The shear is typically your weakest spot because the material can slide over each other, and that is typically the determining factor. So hopefully you learned that stress on inclined surface in axial loading are important. We can look at examples, we can look at justifying failures and other applications. And by the way, you know, all of my material for these lectures are mostly coming from this amazing book, Mechanics of Material by Jure and Brooks. And this is a really good book if you want to have a copy. So hopefully you enjoyed, and I'll see you in the next lecture. Thank you.